National Electrical Code, or NEC, does not explicitly require a neutral conductor for a three-phase system where there are no neutral loads. However, there are three possible reasons why an engineer may require a full-size neutral. Firstly, a neutral conductor provides a return path for ground fault currents, enhancing safety. Secondly, a neutral conductor helps balance the voltage across all phases, reducing voltage drop and ensuring proper operation of the equipment. Thirdly, NEC Article 250.24. A5 requires a neutral conductor if a grounding electrode conductor is connected to the neutral bar. The NEC considers a neutral conductor connected to a grounding electrode as a grounding electrode conductor, or GEC. According to NEC 250.66, the GEC must be size number 4 copper or larger for 2/0 aluminum service entrance conductor. A 4-pole transfer switch is typically used when there is a neutral conductor involved in the transfer. This ensures that all 4 conductors, 3 phases and neutral, are transferred simultaneously, maintaining the system's integrity. Condensing units and chillers typically do not require a neutral conductor because they have no neutral loads. They are usually grounded through their chassis or separate grounding electrodes. In this specific case, the engineer may be requiring a 2/0 neutral for voltage drop mitigation or ground fault protection. If this is the case, it would be prudent to use a number 4 ground wire as well, as the neutral conductor is also serving as a grounding electrode conductor. It is important to note that while the NEC does not explicitly require a neutral for 3-phase systems without neutral loads, it does provide reasons for why an engineer may choose to include one. Ultimately, the decision should be made based on the specific application and safety considerations. Let's delve deeper into the reasons why a neutral conductor might be specified in a 3-phase system, even when there are no apparent neutral loads. The first key consideration is ground fault protection. In a typical 3-phase system, the ground fault occurs when one of the phase conductors comes into contact with a grounded surface, such as the equipment enclosure. Without a dedicated neutral conductor, the fault current path may be limited, potentially delaying the operation of overcurrent protective devices like circuit breakers. A neutral conductor provides a low impedance path for the ground fault current to return to the source. This allows the fault current to rise rapidly, quickly tripping the breaker and minimizing the risk of electrical shock or equipment damage. The presence of a neutral conductor significantly enhances the effectiveness of ground fault protection, particularly in scenarios where the grounding impedance is high. Secondly, consider voltage drop mitigation. While a perfectly balanced 3-phase system theoretically doesn't require a neutral to carry current, real-world systems are rarely perfectly balanced. Uneven loading across the phases can lead to voltage imbalances and increased voltage drop, particularly over long cable runs. A neutral conductor helps to mitigate these voltage imbalances by providing a return path for any unbalanced current. This ensures that each phase maintains a more stable voltage level, improving the performance and lifespan of connected equipment. In situations where the load distribution is uncertain or prone to fluctuations, including a neutral conductor can be a proactive measure to minimize voltage drop and maintain optimal system performance. Thirdly, NEC Article 250.24. A5 plays a crucial role when a grounding electrode conductor is connected to the neutral bar. In many electrical installations, the neutral conductor is intentionally grounded at the service entrance to establish a reference point for the system voltage. This grounding connection is achieved by connecting a grounding electrode conductor, or GEC, from the neutral bar to a grounding electrode, such as a ground rod or a metallic water pipe. When a GEC is connected to the neutral bar, the NEC considers the neutral conductor as part of the grounding electrode system. As a result, the neutral conductor must be sized according to NEC 250.66, which specifies the minimum size of grounding electrode conductors based on the size of the service entrance conductors. This requirement ensures that the neutral conductor can adequately carry any fault current that may flow through the grounding electrode system. Now, let's elaborate on the role of the 4-pole transfer switch. In systems with a neutral conductor, a 4-pole transfer switch is typically preferred over a 3-pole switch. A transfer switch is used to switch the power source of a load between two different sources, such as the utility grid and a generator. A 4-pole transfer switch switches all 4 conductors, including the 3 phases and the neutral, simultaneously. This ensures that the neutral connection is maintained throughout the transfer process, preventing any disruption to the ground fault protection or voltage balance. In contrast, a 3-pole transfer switch only switches the 3-phase conductors, leaving the neutral conductor permanently connected to one of the sources. This can create a potential safety hazard, as it may compromise the ground fault protection or lead to voltage imbalances during generator operation. While condensing units and chillers typically do not require a neutral conductor, it is important to understand the reasons behind this difference. These types of equipment generally have no internal neutral loads, meaning they do not require a neutral conductor to operate their internal circuitry. Furthermore, they are typically grounded through their chassis or via separate grounding electrodes, providing a path for ground fault currents to return to the source. However, it is crucial to consult the manufacturer's specifications and local electrical codes to determine the specific grounding requirements for these types of equipment. Now, let's talk about the specific scenario of a sewage pump station located 600 feet from the building and powered by a 208 volts 3-phase system. Given the distance between the building and the pump station, voltage drop is a significant concern. The engineer's requirement for a 2/0 neutral conductor may be primarily aimed at mitigating voltage drop and ensuring proper pump operation. The increased conductor size reduces the overall impedance of the circuit, minimizing voltage drop under load. Additionally, the engineer may be considering future expansion or changes in load requirements. Including a full-size neutral conductor provides flexibility for adding neutral loads in the future without having to upgrade the wiring. Even if there are no immediate plans for neutral loads, the presence of a neutral conductor can be a valuable asset for future-proofing the electrical system. It is also important to consider the role of the permanently installed generator at the pump station. The generator may have specific grounding requirements that necessitate the use of a neutral conductor. For example, the generator may be configured as a separately derived system, which requires a grounding electrode conductor to be connected to the generator neutral. In this case, the neutral conductor would serve as both a current carrying conductor and a grounding electrode conductor. Given the engineer's specifications, it is prudent to use a number 4 ground wire as well. Even though the neutral conductor is serving as a grounding electrode conductor, a separate ground wire provides an additional layer of protection and ensures a low impedance ground fault path. The ground wire should be connected to the equipment grounding bus at both the building and the pump station, providing a reliable path for fault currents to return to the source. In summary, while the NEC does not explicitly require a neutral conductor for 3-phase systems without neutral loads, there are several compelling reasons why an engineer may choose to include one. Ground fault protection, voltage drop mitigation, and grounding electrode conductor requirements are all important considerations. The decision should be based on a comprehensive assessment of the specific application, load characteristics, and safety requirements. It is always advisable to consult with a qualified electrical engineer to ensure that the electrical system is designed and installed in accordance with all applicable codes and standards. The engineer's expertise can help to identify potential risks and ensure that the system is safe, reliable, and efficient. Additionally, when dealing with sewage pump stations, it is important to consider the environmental conditions and the potential for corrosion. The electrical system should be designed to withstand the harsh environment and minimize the risk of electrical failures. This may involve using corrosion-resistant materials, providing adequate ventilation, and implementing regular maintenance procedures. By carefully considering all of these factors, you can ensure that the sewage pump station operates safely and reliably for many years to come. Always remember to consult with a qualified electrician or electrical engineer before making any changes to an electrical system. Electrical work can be dangerous, and it is important to have the expertise of a professional to ensure that the work is done safely and correctly. Furthermore, local electrical codes may have specific requirements that must be followed. Failure to comply with these codes can result in fines or other penalties. By working with a qualified professional, you can avoid these problems and ensure that your electrical system is safe and compliant. Finally, ongoing maintenance is essential for ensuring the long-term reliability of any electrical system. Regular inspections can help to identify potential problems before they become major issues. Maintenance procedures should include checking wiring connections, testing overcurrent protective devices, and inspecting grounding systems. By performing regular maintenance, you can extend the lifespan of your electrical equipment and minimize the risk of unexpected failures. The information provided here is intended for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or electrical engineer before making any decisions about your electrical system. The NEC, or National Electrical Code, is a comprehensive set of standards for electrical wiring and equipment in the United States. It is published by the National Fire Protection Association, or NFPA, and is updated every 3 years. The NEC is not a law itself, but it is widely adopted by state and local governments as the basis for their electrical codes. Compliance with the NEC is essential for ensuring the safety of electrical installations. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. It also includes specific requirements for different types of occupancies, such as residential, commercial, and industrial buildings. The NEC is a complex document, and it is important to have a thorough understanding of its requirements before performing any electrical work. The NEC is not intended to be a design manual, but it does provide guidance on how to design safe and reliable electrical systems. It is important to consult with a qualified electrical engineer to ensure that your electrical system is designed in accordance with all applicable codes and standards. In addition to the NEC, there may be other local codes and regulations that apply to electrical installations. It is important to be aware of these requirements and to comply with them. Local codes may be more stringent than the NEC in some areas, and it is important to follow the most restrictive requirements. The electrical industry is constantly evolving, and new technologies and materials are being developed all the time. It is important to stay up to date on the latest trends and developments in the industry. This can be achieved by attending industry conferences, reading trade publications, and taking continuing education courses. By staying informed, you can ensure that you are using the best practices and technologies in your electrical work. Safety should always be the top priority when working with electricity. Electricity can be dangerous, and it is important to take precautions to avoid electrical shock or other hazards. Always energize circuits before working on them and use appropriate personal protective equipment, or PPE, such as gloves and safety glasses. It is also important to follow lockout-tagout procedures to prevent accidental re-energization of circuits. By following these safety precautions, you can minimize the risk of electrical accidents. The information provided here is intended for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or electrical engineer before making any decisions about your electrical system.